Okay, let's talk a little bit more about absorbing Markov chains. From our earlier discussion, we found that successive state matrices of regular Markov chains always approach a unique stationary matrix. In other words, changing the initial state matrix does not change the stationary matrix that it's going to approach. So consider the transition matrix from the above problem, along with two different matrices we obtained from parts C and D of the problem. So remember, this was our transition matrix, and we actually had two different state matrices here, 1.4.6 and another we'll call S prime 0.7.3. Okay, let's see what happens. If we multiply S times P, notice that we get back S. And notice if we multiply S prime times P, notice that we get back S prime. Okay, so we actually have two stationary matrices there for that transition matrix or that Markov chain. And actually this absorbing Markov chain has an infinite number of stationary matrices. But changing the initial state matrix for an absorbing Markov chain can cause the successive state matrices to approach a different limiting matrix. Since absorbing Markov chain can have many different stationary matrices, we cannot expect this approach to work with an absorbing Markov chain. So basically, we have to find a different approach. However, the transition matrices for absorbing Markov chains do have limiting matrices, and they're not too difficult to find. So let's go back to our diagram of the way the standard form of an absorbing Markov chain is partitioned. So we're going to partition it like this, I, the zero matrix, R, and Q. Well, it turns out that the limiting matrix P to a power, if we pick a high enough power, approaches a limiting matrix P bar as K increases, and P bar is actually this matrix. Now notice that this matrix is I here in this quarter, 0 in this quarter, 0 in this quarter, but it has FR in this quarter. So what is FR? Well, FR is the product of F and R, where F is this. Now this is getting a little strange, isn't it? F is the matrix I minus Q inverse, and this is called the fundamental matrix for P. And I, of course, is the identity matrix. Now, so if we know I, R, and Q, then we can get P bar, because I is here and FR is just based on I and Q. So, and R, of course. So we can figure this out. So let's see, it takes a few steps to do it, but we can do it. So we've got this matrix partitioned to where we have the non-absorbing matrices first, and then the absorbing matrix, the absorbing matrix first, and then the non-absorbing down here. Now, notice here, this is the 2 by 2 identity, so that's I. And here is the zero matrix, so that's the zero matrix. And so this has to be R, and this has to be Q. Okay, so now if I want the limiting matrix, I know I is going to go here, 0 is going to go here, 0 is going to go here, but I need to figure out what this matrix FR is going to be. But before I can multiply F times R, I got to find F. Well, F, remember, is I minus Q inverse. So we know since Q is just a 1 by 1 matrix. So the identity for a 1 by 1 matrix would just be the number 1. So now if I take I minus Q, that would just be 1 minus the 1/2. So 1 minus 1/2 is 0.5. So that's Q. Now, finding the inverse of a matrix can be tricky, but if it's just a 1 by 1 matrix, it's simply going to be the reciprocal of the number. So in this case, since I minus q is a half, then the inverse of I minus q is simply the reciprocal of a half, which is 2. So I minus q inverse is 2. I still have to do one more step to get FR. I have to multiply F times R. So I take the F matrix, which is 2, and remember the R matrix was 0.2, 0.3. So I multiply those together, and I get 0.4, 0.6. So now I can put it back together and get the limiting matrix. So notice here I put the identity matrix, the 2 by 2 identity I put the 0 matrix here, I have a 0 matrix here, and I have the FR matrix here. And so now this is my limiting matrix. Now we can now use this matrix to find the limit of successive state matrices for different state matrices. So let's say we have a state matrix 0, 0, 1. Well, all I have to do to find the limit is multiply that 0, 0, 1 by this limiting matrix. So 0, 0, 1 times that is just going to give me 0.4, 0.6, 0.0. But if I multiply this matrix by it, it's going to give me 0.7, 0.3, and 0. And that agrees with our earlier result for those matrices, S's, that were associated with those state matrices. Now, something that's interesting is this F determines the average number of trials that it takes to go from a non-absorbing state to an absorbing state. So since F is 2, in our example, it means it will take an average of 2 years for an owner to go from state C, where they own an estate, to one of the non-absorbing estates where they sell the estate. Now, some will do this in 1 year and others will do it more than 1 year, but the average time is 2 years. Now, here are the properties of the limiting matrix. If P is a transition matrix in standard form for an absorbing Markov chain, and F is the fundamental matrix, and P bar is the limiting matrix, then the entry in row I, column J of P bar is the long run probability of going from state I to state J. For the non-absorbing states, these probabilities are also the entries in the matrix FR used to form the limiting matrix. And then finally, the sum of the entries in each row of the fundamental matrix is the average number of trials it will take to go from each non-absorbing state to each absorbing state. Okay? Now, let's take a look at our transition diagram for the part-time student problem. Okay? It says, in the long run, what percentage of entry-level students will graduate? What percentage of that should say advanced level students. So what percentage of advanced level students would graduate? Okay, let's see. So I took the transition matrix in standard form and I divided it up into the identity matrix here, the 0 matrix here, and this is R and this is Q. Now, I minus Q, I just take the identity matrix, this identity matrix, and subtract Q, and I get 0.4 minus 0.30, 0.5. I found the inverse just using my calculator. So I got 2.5, 1.5, 0, and 2. That's F. And now I want to multiply F by R, so I multiply F and R together, and I get FR. So now I can get my limiting matrix. Remember, my limiting matrix, I'll have the identity matrix here, 0 here. I'll put FR here, which is this matrix I have circled here, and then 0 here. So now, answer to A, it says, so I want entry level to graduate. So what percentage of entry level will graduate? Well, entry level to graduate is right here. So that would be 60%. And then advanced level to graduate would be 80%. So we would expect 60% of the entry level to graduate and 80% of the advanced level to graduate. Now, what's the second question says? It says, what is the average number of years that an entry level student will remain in the program, and what's the number of years an advanced level student will remain in the program? Okay, so if you look at the first row, in F. Let's find F. Where's F? Okay, here's F. So if you add 2.5 to 1.5, that's the entry-level students, that's going to be 4. So this indicates that an entry-level student will spend an average of 4 years in the transient states E and A before reaching an absorbing state. So, in other words, graduating. And then if you sum the second row, 0 and 2, you get 2. So this indicates that an advanced level student will spend an average of 2 years in the transient state before reaching an absorbing state. And that would be graduating or dropping out, actually. So you can see that these Markov chain examples are a little bit complicated, but they're also very interesting. I want to end here with just a couple more calculations for you. I'll let you read this on calculations, and then I'll just show you what I did here. When I took this matrix and raised it on a calculator to a very large power, say to the 50th power, I actually found that I got the limiting matrix P bar. So it's interesting that when you take that transition matrix and raise it to a large enough power, it does eventually converge to that limiting matrix. But a couple things before using this to P to a power to approximate P bar, be certain that P bar exists. If you try to approximate a limiting matrix that does not exist, the results can be misleading. So here's a transition matrix, and if you say you compute P50 and P51, so I put this in a calculator and I got P to the 50th power, and then I put it in and got P to the 51st power. And if you do further calculations, it shows that the even powers will give you results similar to the first matrix, and odd powers give you the results similar to the second matrix. So again, we've got that oscillation of it flipping back and forth between the two types of matrices. So in this case, the transition matrix does not have a limiting matrix. And so that's pretty much the lecture on Markov chains completed. And if you want to study them further, you can do some research online. Good day.